Good afternoon, people who have joined us today, both on Zoom and in person. Today we'll be going over the training of optimal large language models paper, which was published by Google DeepMind in 2022. This paper is very highly relevant in the current landscape of LLM research, and it deals with a very critical issue of scaling, the scaling problem essentially. What we were observing until this point was the assumption that bigger is essentially better. And by bigger, I don't mean the current standard that we have of having bigger data sets or having more weights, having more tokens. This bigger was just okay. We have a bigger model essentially, and it doesn't matter what kind of data you train it on, it just has to be bigger. And it was an assumption that it'll just outperform everything else we have. But like we realized with the whole deep seek scarcity that we had, it was very clearly understood that more than just your parameters, what matters is the number of tokens you're using, the kind of architecture you're using, the layers that you're using, and most importantly, the kind of data you are using. A little bit of a background on why I think that I can also talk to this topic is I'm a senior in computer science, and I am currently doing a Fury research with the data mining and machine learning lab at ASU. It's one of the most prestigious machine learning labs, I think, in the country. And the principal investigator or the mentor that I work with, he is getting his PhD under Professor Huan Liu. He is a Regents professor at ASU, and he has been working on feature selection and machine learning for about better half of like a 45 year career that he has had. He has about 120,000 citations, one of the highest in the field. And I think among the top 10, like across all citations by all professors at ASU. So, they work on deep learning, machine learning. And currently, what we are working on is causality and few shot learning. So, the whole point of few shot learning is undermining this very assumption that a model needs to be very big, it needs to be very huge. It's undermined by this simple fact: if the quality of your data is good, then all you need is a good model, some good lines of code, and what really matters is the kind of data set that you're using and the way that you're using to train this like model, the kind of architecture that you have essentially. Anyways, coming back to um, training compute optimal large language models, the paper that we'll be going over today, collectively known as or like referred to as the Chinchilla model or the Chinchilla paper. It's, as I said, it's titled Training Compute Optimal Large Language Models, which was published by Google DeepMind in 2022. It was authored by about 13 people. And amongst these, as in the first author or the principal investigator for this paper was, it's credited to be Jordan Hoffmann, who is, as I said, often cited as the first author for this paper, and along with other DeepMind researchers such as Sebastian Bourgeois, Arthur Mensch, and some others. If I were to like encapsulate some ideas here, I would say something like BERT, which is a very commonly known, it was a frontier language model. Falcon, which is also one of these frontier models, and Llama, which is one of these frontier models. We see that they came along after the discussion produced by the Chinchilla paper. As I said earlier, before this frontier, we were only concerned with a bigger paper, a bigger model means better output. But soon we realized that, I mean, after this paper, that when your data set size increases and the number of tokens that you're using increases, like the Chinchilla paper, the model that has been trained here, it has 70 billion parameters in it and about 1.5 trillion tokens. The performance that was observed was significantly higher, and the papers that had come before it, they were significantly being undermined by the context that was given by this model. Before we begin diving into the concepts discussed in the paper, I would like to discuss just some good practices to actually read this paper, something that I found myself while going through this paper. It's essentially like a 45-minute guide to looking at like any research paper. I don't know if you guys have a lot of experience reading research papers, but this is how I would do it. Usually, if I look at a paper like this, oh, also, by the way, the link to this paper is sent on the Discord announcements. So you should be able to find it over there. It's a 36-page paper. I mean, yes, 10 of these pages are probably going to be citations, but the meat of the paper is always going to be in the abstract and then the introduction. That's where you get most of your information. Some of the parts talk about related works, which is essentially describing what works you are actually citing and why you are citing them. It's a very important part of having a research paper, because you have to tell what you're building on and what you're trying to benchmark or go against. And then you have the experiment methodology and your experiment features, how you're conducting that experiment. If someone were to reproduce this experiment, how would they do that? The GitHub repository for running the code. So that is how the people verifying the paper or giving peer reviews, they would like go over these papers. You would have that section too. So anyways, that's like how a paper is defined. After the experiment definition part, you have the results section. There's a table that will essentially say that, oh, these are the benchmarks that I used. Benchmarks is essentially any previous paper that you cite, and then say that, hey, these are the findings of that paper and this is what I'm competing against. So these are my findings against these findings. So these are some benchmarks that you would have. And after that, you just give a conclusion. If you're funded by someone, you say that, yes, this was funded by this grant, and that's how you land into the references section. So that's a basic structure of a paper. Anyways, in the announcements tab, I have just sent the link to the archive for this paper. Starting next session, we'll probably just have a separate channel for this, so it'll be a little more unified. I'll also send for a deeper understanding on this topic itself. Recently, I was watching a podcast by the Lex Friedman podcast, and it was with Andre Karpathy. He's one of the leading minds in LLM research and just artificial intelligence research in general. Some people even say that if you want to keep up with what is the frontier, just read and watch everything that comes out of Andre Karpathy's brain. So, keep following him on Twitter. He's the forefront. He completed his PhD from Stanford, and then he was at XAI as head of their AI initiatives. And then I think he also had a major role in creating some policies, workflows, hiring people at OpenAI. Larry Page, Elon Musk, and Andre Karpathy, these three are some big players that we have known in the creation of OpenAI. And obviously, we all know the Nobel Prize winning scientist, Demis Hassabis, who is also the CEO of Google DeepMind. Anyways, moving forward. If I were to give you a recommendation for reading this paper, which I'll go over in the next 5 minutes, it would be something like this. Usually aim for 3 passes on a paper. Since it's a 36-page paper, and say 20 of these pages contain some substance that you actually want to learn from, what you want to do is you want to have a 10 to 15 minutes first pass, which is a big picture of the paper. You can do it by yourself, or you can also do this with the help of an LLM. A good tool that I can recommend is Alpha. So the Alpha, if you know what AlphaFold is, they also ended up creating an Alpha XIV, which is the AI companion version of Archive, where you can essentially prompt any forefront like model, like say, Quen or like Gemini 3.0, whatever. And then you can essentially give it the link to a paper and give it a prompt and it can start like, talking to you or teaching you the paper or whatever. Anyways, so I recommend reading the abstract and the introduction very, very carefully, like I said before. Skim the related work to see how it contrasts with earlier scaling laws. And one important paper that is mentioned is the Kaplan et al., which came out in 2020. You should also look at the key figures and tables. So, this is what your first pass in 10 to 15 minutes should be. The abstract, the introduction, and then, just skimming over the diagrams and the findings. Don't go too deep into it. Now comes the second pass, because you have roughly like an idea about what this paper is about, where it came from, what it's trying to do and stuff. So you do a second pass, which is reading the sections on the scaling law estimation, which will be right after the introduction. So like, right after the introduction and the related works, they talk about some concepts that they are discussing. So you talk about the scaling law estimation and computing and compute optimal frontier in detail. So, here's when you start going into the meat of the paper, the formulas and the functions. You also spend some time on the experimental section where they actually train the chinchilla and compare it. So you don't have to reproduce every paper that you study because, of course, you won't have the kind of compute resources that a company like Google DeepMind would have had in 2022. They were essentially forefront of all AI work happening in the world at that time, alongside up and coming OpenAI and NVIDIA research. But we have to understand that at that point they had, like in the field of AI, they had pretty much like unlimited access to compute, money, resources in terms of like energy and GPU hours. And of course we can't reproduce it, but like we can try to do something like smaller, right? At least understand what the experiment is. Go through the code maybe. And then once you do that, like a little deep like dive, you go for a third pass, which is not necessarily 100% recommended, but say if you want to do a project, you see the appendices for the model details, the specifications, say like Quen, 1.5 billion parameter, or Gemini 70 billion parameter. Like just go through the specifics so you have like these numbers you can keep up with. You go through the data sets that they are using. For reference, the research that I'm doing right now, I mainly deal with only 2 data sets. But the thing is, I know these data sets in and out. In fact, I had to look at the launcher file for specifically this data set in our code base. And then all I would do is understand what this data set is, why it was created, what are the tasks you can do with this data set. You have to know in and out if you're truly trying to do some research work. Anyways, and as I said, that is why this is for projects. You read the appendices for model details, data sets, and training hyperparameters. What essentially are they doing? Are they freezing a model? On top of that, are they creating a classification layer? Are they trying to do like a different kind of architecture? So you need to understand that, like, what are the fine tuning that is happening? What is like the hyperparameter tuning that is happening if you plan to reproduce or extend the work? So this is where a research or a project-based mindset would come in. Anyways, after these 3 passes are done, you should also focus on what to skim versus what to focus on. Essentially, you want to put a very deep focus, and this is just for this paper, on the formulation of loss scaling law and how model size, like NNN and data, like DDD, are related. So we'll come across like a formula, which essentially is the formula for calculating like how much time in GPU compute hours it would take if you had n number of tokens, D number of parameters, and then C number of compute. There was something, but there's a clear linear relation where you can multiply the variables, and that's how you get the loss scaling law and model size. You should also look at the compute optimal frontier, how they define and estimate the optimal trade-off between parameters and tokens, which are the 2 most important things here. You should also look at the Chinchilla versus Gopher results. Gopher was the previous one, the paper that I was just talking about, and Chinchilla is this one, the 70 billion parameter, 1.5 trillion token model, especially in the flops matched comparisons across benchmarks. Something that you can skim in this paper is literature review and some benchmark tables, because this is the frontier. And unless you need specific numbers, like, you're actually trying to like dethrone, like, Chinchilla, which is not going to happen right now. But you want to reference previous work too. Unless you want to do that, you need to, skim literature review on this paper. And you shouldn't look at like very detailed per task evaluation tables. Focus instead on aggregated metrics like the average accuracy, and that would be more helpful. Another set of prior knowledge tokens that I'd like to give you before, see what I did there, before we start this paper would be you should be able to extract the most amount of wealth from this paper. If you're already somewhat comfortable with what a transformer architecture is, what is LLM pre-training or fine-tuning, the basic idea of auto-regressive language modeling with next token prediction. This is not that deep. It's just like, what a transformer architecture is and what LLM pre-training is, feature selection, creating your data set, and just knowing that an LLM or like a transformer, which is usually built these days on a transformer architecture, is essentially doing a next token prediction. It's just a prediction machine. And scaling laws, like empirical relationships, like loss improves as a power law in model size and data. We'll go over this. And what a flop is. Like, you must have heard that, oh, a new NVIDIA GPU came out which has like, X teraflops or whatever. So, this like flop, this handling of number of instructions. So what it means to fix a training compute budget and compare models at equal flops, right? Anyways, you don't need like heavy reinforcement learning, diffusion, or advanced optimization theory for this paper at all. As I said, this is like frontier work. Think of it like if I were to create like a very fine-tuned model that can essentially just look at like, a disaster image and tell you what disaster it is. That is like a very hyper finely tuned like model just to do that task. But say if I were to take like, I'm not going to say Gemini because Gemini is very strong. But say like if I take like ChatGPT, like 3.0, it's a general model. It's a general purpose model. Of course, it won't be able to tell like things as like pinpointed as like my disaster classification model. But this is a foundation model that can tell you about a bunch of things that my model simply cannot, because all it does is tell you about disaster classifications, right? So you don't need to know about a lot of like heavy reinforcement learning, diffusion, or advanced optimization. Just remember that this paper is like talking about creating a frontier, and that's why we are discussing it. There are some key figures and results in the paper that I'd like for you to that I would like for you to watch out for. Like I said before, the figure table where Chinchilla, which is a 70 billion parameter, 1.4 trillion tokens, is compared to Gopher, which was a 280 billion parameter. See, bigger model, not necessarily better, and others at equal training compute, flops. Chinchilla wins on most benchmarks. The MMLU result, where Chinchilla achieves around 67.5% average accuracy, significantly beating Gopher. And also the scaling law fit plots, which show how loss behaves as model size and data increases, and where the compute optimal frontier lies. There's also some common traps and misinterpretations that I'd like to clear right now, so that we don't have to think about this going forward, which is Chinchilla says, I mean the paper says, that small models are always better than big ones. This result is conditional. While we do say that necessarily being larger does not mean better, similarly being smaller also does not mean it's better than the bigger models. The result is conditional, as in for a fixed pre-training compute budget, many existing models were too large and under-trained. This is a recurring theme that we'll come back to. If you also care about inference cost or deployment scale, the trade-off can change. Okay, so it really just comes down to what is your purpose? What is your resource allocation looking like? Are you like an established person in the field trying to solve a specific problem, or are you trying to build a general purpose model that can solve a bunch of problems? You don't care too much about accuracy. You just want to, make a $20 per month membership, thing like ChatGPT or whatever. It's pretty useless. I pretty much use it only for creating prompts for other LLMs, which is like insane. And it just depends on what you're trying to do. for example, in my lab right now, we are literally like our whole training corpus is like 8 images per disaster. So like these people, they're probably training their data sets on like trillions of like, images or whatever, like, to have like a large corpus. For us, we are just doing few shot learning, which is like 8 images of a landslide, and then we show it pictures of landslides, and it just gives us like a 95% accuracy, which is insane. But yeah, it just depends on what you're trying to do and what your goal is. Another thing that we talk about is, which is a common misconception, is the law says that 20 tokens per parameter is universally optimal. As I said about the equation, right? There's a relation that can be made, but like in the Chinchilla paper, it says that the law will state that 20 tokens per parameter being used, so 70 billion parameters, and then 1.5 trillion tokens that I was talking about. So essentially, if you have one parameter, you should have around 20 tokens, is universally optimal. This paper suggests an approximate linear relationship and a regime where around 20 tokens per parameter is near optimal, but optimal ratios can shift with architecture, data quality, and objective. Now, hear me out on this. Training GPT-5 took about 6 months. And just think of it this way. Had you moved 20 to 19, what do you think happens when we are dealing with like multiple hundreds of petabytes of data, right? Like while training a model. If you move from 20 per parameter to 19, your training time can get like cut down by a significant like amount. What does that mean? It means that significantly less energy would be used. Your accuracy and performance will change. Your costs for electricity is going to go down. Your GPU compute hours, the number of people who are going to be working on that will definitely get paid. It changes. And if I were to do the same thing with 20 to 21, it just increases on a different, like multiple hundreds of millions of dollars of difference can be created by this like one small change. So you can't really do that. And what we need to be thinking about again is creating like a smaller experiment, and that's why these people get paid so much, because you just need to understand that there's trade-offs for what we are doing, and we need to understand that it's not that linear like the way that we are thinking. Anyways, this solves scaling once and for all. Once and for all is a very dangerous thing to say, like in academia at least, because that's what PhDs are built on. A PhD is essentially finding a new frontier, deciding that you need to do a new experiment, and then pushing the frontier forward by creating or adding something new to the field. That is literally what a PhD is. In order to get a PhD, you read everything there is to know that you're doing your PhD in, and then contributing something meaningful that pushes the frontier just a little. This is the circle, you are the small thing, and then in this circle you're just trying to create like a small dent upwards, and that's how you earn your PhD. And once and for all is dangerous, because we have all heard about the different atomic structures of the atom, and like how people thought that, oh, like an atom is an indestructible entity. But then came like a model where we thought that, okay, electrons are like in a fixed position, and then we came up with, okay, no, that is not possible because electrons are probably like spinning around. And then came like another experiment which stated that, oh, there's something at the center of the atom too, because we can't like fully pass through. And then came like another idea that, oh, the nucleus actually has both neutrons and protons, and the electrons are going outside. And then came the valence electron theory and all that, whatever. So once and for all is not a real thing. One thing today, and sure, it's based on everything that we have known so far, but it can change. Things change. People find new things, and we keep moving forward. So the law is empirical, estimated on a particular model family and data mix, and it is a guide, but not a theorem. A quick reading checklist. What is the exact question that they are trying to answer here? This is one thing that we'll be looking at. Compute optimal training trade-off between model size and data. Very central question. Another central question is, what are the key variables and how are they measured? As in loss, flops, parameters, and tokens. What is the main empirical relationship claimed, which is loss versus the number of tokens and the power law that we are talking about. And how do they validate the claim, which is the new model training benchmark suite? And under what assumptions or regime does the result hold, which is the model class token range data distribution? We'll just go over this. Extracting the central contribution in from this paper. So what is actually the problem statement? So you can see, given a fixed training compute budget, which is the flop, what is the optimal combination of model size n and training tokens d? So there'll be like a relationship between that. Are current large language models compute optimal or systematically undertrained or overtrained? And why it matters. A factor of two mistake in an allocation can cost millions of dollars in wasted compute. Don't move to the next slide. As you can understand from what we have been going over, you can look at the abstract and underline the claim about compute optimal model size and tokens. You can find the paragraph that defines the recommended scaling rule, which is roughly model size and data should be scaled together, and many prior models were undertrained. If you look at the Chinchilla versus Gopher comparison table figure to see that a 70 billion model trained longer beats a 280 billion parameter model trained less at fixed compute. From that, you already have smaller but better trained models can dominate large undertrained models at the same training compute. I'll only say one word, DeepSeek, and that should just answer it, right? What they did is they had scarce compute, but what they had was good data set quality. They had suboptimal compute compared to the big guns here, but they did have good data sets. What they did is few shot learning, but also good feature selection, and they were able to outperform. And it literally did create like a panic, like in the, I don't know if you remember the small panic at that time where Nvidia stock just dipped for a while, but whatever. If I were to put it in one sentence, for this to be placed, its placement in the AI trajectory, I would say that this paper marks the shift from bigger models are always better, like I said before, for a given compute budget, data and training schedule are as important as parameter count, and many flagship LLMs have been undertrained. Let's go over the core ideas, contributions, and claims made by this paper and the intuition. If I were to give a plain English summary for this paper, just in plain words, this paper finds an empirical rule for how big a language model should be and how much text it should see. If you fix the total training compute, using that rule, the authors show that many famous LLMs were trained on too little data for their size, and that a smaller model trained on more tokens called Chinchilla can outperform them across a wide range of benchmarks while also being cheaper to run. Let's go over the problem statement one more time. Precisely, given a fixed pre-training compute budget, roughly the total flops, what is the optimal combination of the number of parameters, that is n, the number of training tokens, d, such that the validation loss is minimized? And are current large language models close to this compute optimal trade-off, or are they systematically undertrained or overtrained for their size? This is in regards to 2022. Why does this problem matter? I think that this problem matters because training LLMs is extremely expensive. Even a factor of two mistake, like I was talking about, how you allocate compute between model size and data can cause millions of dollars in damages. I mean, sure. Many research groups and companies were scaling model size much faster than data set size, quality of data. You can't just crawl all the data in the web. That's what we did. And we have just a bunch of garbage data and we don't know what to do with it. What you need is people who can do feature selection, people who can do data engineering, people who can make these data sets come together in a way that you're able to standardize it and train a model that is able to learn something from this deep learning. A robust scaling law essentially lets you plan training runs more efficiently. It helps you decide whether to collect more data or to buy more GPUs. It helps you interpret why some models underperform despite being huge. What are some of the main contributions given by this paper? Basically, I'd say that I can put that into four categories here. One would be re-estimating the scaling laws for transformers that jointly model how loss scales with both parameters and training tokens over a wide range of sizes, roughly the 5 billion to 500 billion token range, and many model sizes. Another would be derivation of a compute optimal training frontier. Next slide, please. Showing that for a fixed compute budget, you should scale model size and data volume roughly in proportion, leading to a near linear relationship between N and D. The demonstration, third one, the demonstration that many existing LLMs are undertrained, quantifying exactly how models like Gopher and GPT-3 are from the estimated compute optimal frontier. And finally, training and evaluation of Chinchilla, a 70 billion parameter model trained on about 1.4 trillion tokens that at equal training compute outperforms much larger models up to 200 to 530 billion parameters like we'll see in the table on a large suite of benchmarks and uses less inference compute. Let's go over the high level method architecture for this paper. Um, you can go on to the next slide, please. This is the scaling law that we were talking about. Okay, let's go over the high level method architecture. This paper system is a conceptual rather than an architectural. It's food for thought. It's not necessarily hard coded theory, but thought engineering, if you will. The kind of sphere where actually Andre Karpathy works in both. He's also a very highly technical person, but he does a lot of thought engineering. Like lately, he has been thinking about. I think this was like actually 2 years ago. He has been thinking about intelligent life. Like a lot of AI at Tesla, it deals with not really just getting as many GPUs as you want, and like having the biggest rig to train the largest GPU on the largest GPU cluster, having a bunch of like N100s or whatever. They are trying to like re-engineer the way intelligence emerged. As in like if you have a child, and we have gone over this in a previous arc session, it is essentially created with a blank neural net, and there are some predefined weights which are your evolutionary like parameters that you're born with. But essentially, what happens is that as a child is going through life, these parameters are fine tuned with the experiences that this child has, and you can see it happening in real time. And that is how intelligence emerges. I mean, intelligence that was always present in this neural net is hyper tuned and goes forward, right? It essentially becomes a better neural network, and then you end up like giving a lecture or whatever. But like that's how human beings like become smarter. uh he's actually going over this, that all life is essentially like chemical processes, biochemical processes, and all life like at least on earth like started with chemosynthesis and high temperature aqueducts where single celled organisms would like be there, and they would do chemosynthesis, and then one of these ate a chlorophyll, and then it just started doing photosynthesis, and at that point they became like they realized that, oh, this is cool, and then they started like replicating in large numbers. They became so abundant that they are potentially impacting the ecosystem on earth because they are creating too much oxygen at this point. And then like the whole ecosystem itself is changing. New organisms are emerging that are more efficient at using this oxygen to survive. And then it goes forward like that, and more and more diversity comes along. Of course, plants take on first, and then aquatic life takes on. Aquatic life is able to move on to the like ground now, which has been fixed by these plants that were growing because of the earlier descendants which ate the photosynthetic material. And that's how like life emerged. But what was it, right? Like it was a bunch of like single celled organisms or whatever it was that were just trying to like replicate based on the source of energy that they had on the aqueducts. So now think of it from that perspective. How many of these planets, like in the identifiable like space, could have similar aqueduct with temperature coming from the core and some chemicals trying to be together like organic matter. So intelligence can emerge like that, and you leave it long enough, you can end up giving a lecture on it. It happens. That's how intelligence emerged, and it's really not that deep. It can happen anywhere. So if you think about intelligence from that perspective, it's easy to understand that there's a chemical link to it, and something like that is happening. But yeah, see, if you think about AI from that perspective, it becomes different, right? It's not just creating a model that can just look at it's like N100 clusters that just you feed it a bunch of data and then it just that is like one application of it. That is not general intelligence, right? Like what is general intelligence is what I was trying to actually get to. This is general intelligence, to be able to take these topics, synthesize information, talk about it, and then after all of that I still have my as an organism I have goals, right? And then as a person I have goals in the system that I'm actually living in. So if you think of it from that perspective, AI is a artificial general intelligence is a different kind of problem. But yeah, moving forward from there, in this paper, architecture that we are discussing, we also want to find a fit for an empirical scaling law that predicts validation loss as a function of n and d. We also want to combine this with an approximate formula for compute. And we also want to use the predicted optimum at the Gopher compute budget to design and train a specific model Chinchilla and evaluate it. The underlying transformer architecture is fairly standard, decoder only and dense, and not the focus. The novelty is in how training allocation is optimized. Okay. Before I talk about this slide, I just want to go over some of the intuition behind this work, which is how this method essentially works. What we are doing is, as I said before, we are doing a large grid of experiments. We are going to be running a large grid of experiments. We train a variety of transformers, language models with different sizes and training token counts on the same data distribution. Record their final validation losses. So a variety of transformer LMs with different sizes and training tokens on the same data distribution and record their final validation losses. We also fit a scaling formula. So we model the loss as something like it's a formula. I'll put it in the another document. But we find this loss, and in this relevant regime, we want to capture the diminishing returns from increasing parameters for tokens. Just remember that diminishing returns from increasing the parameters for tokens. Parameters, as in model size, increasing the model size. That is the villain here. We also want to look at the approximate computation cost. So for transformers, training flops scale roughly like C proportional to NDC, right? We just looked at that formula one more time, up to constants. And then we also want to look at optimizing under a compute constraint. So if there's a fixed C, what pair of N and D minimizes the loss, and what is the best outcome given a constraint? Because as I said, different organizations have different resources, different needs, different problems that they're trying to solve. Different investors will pull back funding if you don't do specific work. You also want to interpret and compare this to existing models, which is place the existing models like GPT-3, Gopher on the ND and the ND plane and compare them to the predicted optimal curve. Many lie above or beyond the optimal, indicating undertraining. We're also going to be looking at two more things: training a compute optimal model, which is for the compute used to train Gopher. The frontier suggests a model about 4x smaller trained on 4x more data. And that point defines Chinchilla, 70 billion parameter, 1.4 trillion tokens. And evaluate and validate this, the last one, which is show that Chinchilla beats Gopher and larger peers on a wide set of language benchmarks, confirming that the compute optimal recipe works in practice. Okay. I'm not going to be going over math because if you want to do that, you can go over the paper. But let's look at the concrete analogy that I can go over here. Essentially, think of training an LLM like studying for an exam with a fixed total number of study minutes. Model size N is your brain size or the number of neurons. So model size N is your brain size, which is the number of your neurons. And data D is the total study material, pages or problems that you have to work through. Okay. Compute budget C is the total study hours, which is brain size times hours spent. That's compute budget. If your brain is huge, big brain, but you only skim a few pages, you are undertrained and waste potential, right? If you have a small brain but read endlessly, you also hit a diminishing return, point where you forget and you overload. There is a best balance of brain size and pages read for a given total study time. And this paper finds that balance for transformers and then validates it with Chinchilla, which is their model. Um, let's look at the novelty relative to, prior work, which is essentially like prior scaling law work, like I was saying earlier, in the paper Kaplan et al., mostly assumed a fixed data set and varied model size for or vice versa. So a fixed model size and varying data set sizes. Um, Often recommending very large models trained on relatively few tokens per parameter. This paper jointly was able to fit over both parameters and tokens and explicitly optimizes under a compute constraint, shifting the recommendation toward a more data and somewhat smaller models. It does not just propose the law, it trains a real model, which is Chinchilla, at the predicted optimum and shows strong performance gains in practice. Okay. What this paper does not deliberately does not attempt, let's go over that also because it's important to see what this paper is not doing. It does not propose a new architecture or attention mechanisms. It keeps the transformer architecture standard. The transformer architecture is attention is all you need, is what that paper was called, the transformer paper, right? It's as is, it's all good, it's chilling. Andre Kapati loves it. It does not address RLHF, safety fine tuning, or instruction tuning. The focus is pre-training, okay? Data pre-processing, getting the data set, putting it together, finally creating a balance between CDN, right? And it does not solve long context modeling, sparsity, or multimodality, right? All of that is not this paper's concern. Also, my work is also on multimodality. So we are doing image and text. All results are on text, language modeling, and standard benchmarks. Okay? If I were to create an elevator pitch for this paper, it would be this paper essentially asks, if you have a fixed training budget and flops, should you spend it on a very large model or more data? By fitting empirical scaling laws for transformers over parameters and training tokens, the authors show that many large language models are too big and undertrained, like we were talking, and that a smaller model trained on more data can be strictly better. They trained such a model called Chinchilla. Again, 1.4 trillion tokens, 70 billion parameters, which outperforms much larger models like Gopher, GPT-3 on a wide range of benchmarks while also being cheaper to run, right? Okay, now let's go over some of the technical mechanisms for this paper. Let's move a few slides over to practical implications for training. And while you're just looking at that, let me go over some technical mechanics for this paper. Essentially, some key definitions and concepts that I would like to go over. And by the way, we are done with the meat of the stuff that we were going over. I'm just going to be giving you a few knowledge points and then be going over some of the deeper stuff which comes in the second and third run, but is not really very necessary. The main ideas have already been conveyed. So if you feel like leaving, you can leave. I'm just kidding. Key definitions and concept for this paper. Parameters n are the number of learnable weights in the transformer. Learning tokens D is the number of tokens processed during pre-training. Compute budget C is approximately the approximate total number of floating point operators, flops, used during training for dense transformers. So, C, N, and D, and flops. Scaling law, an empirical relationship showing how loss decreases as a power law with increasing model size and data. That is the scaling law. That's what this paper is. An empirical relationship showing how loss decreases as a power law with increasing model size and data. Another definition is compute optimal frontier, which is a set of ND pairs that minimize loss for each possible compute budget. Points of this frontier are suboptimal. Points off of this frontier are suboptimal. These are the things that we have to talk about. Let's talk about the training setup and pipeline, the architecture family. We use decoder-only transformer language models with standard components like a multi-head attention, feed-forward layers, layer normalization, and it's pretty much similar to Gopher. So, read that paper if you want to. The objective is next token prediction, obviously, with cross entropy loss. So CE loss over a large text corpus, large data set, cross entropy loss, next token prediction. That's what we want to do. Not that deep. Training loop. The training loop is going to be sample mini batches of token sequences from large web, books, other text mixture. So similar to Gopher style, often referred to as massive text. So massive text data set. We are going to be doing a forward pass through the transformer, and then compute the cross entropy loss. We are also going to be doing a back propagation and update the weights with a variant of an Adam optimizer. So an Adam optimizer or a similar optimizer, schedule the learning rate decay over total tokens and budget. So this is what the architecture is like. Very simple, very standard. We do this in almost all LLM research even today. The key twists are not in the pipeline itself, but in the range of NND, the pair combinations explode and how they are analyzed. Datasets, benchmarks, and evaluation metrics went over in this paper. So the pre-training data, like I said, was a large deduplicated text corpora combining web crawling, books, code, and other text sources following the Gopher or massive text style. The evaluation benchmarks are going to be language modeling, which is on held out text data set. So usually what we do is we take like 3 classes that we train on, and then we hold out one class, and then we test, and then we see what the loss is like. So that's what holding out is. Like, say I'm training a model that can do disaster classification. So I'm giving my example here. There's 4 types of disasters in our data set: hurricane, earthquake, wildfire, and let's just say there's one more. Okay, typhoon. Okay. So say I do like the first 3 for training, but I hold out one. Then this is what this architecture is trying to do. There's also other NLP tasks like question answering, reading comprehension, and closed tasks. Which are often evaluated in 0 shot or few shot settings. Few shot is again small corpora. You give it a small, like, give me 8 images of flood and then ask me by showing me any image of a flood, and am I able to tell if it's a flood image or not? That is few shot learning. Okay, and then metrics that we do. So as I said, cross entropy loss, right? And then the log. Lower the better. The lower the better. We all want low loss, right? The higher accuracy. And then we want accuracy on benchmarks like MMLU. The higher the benchmark, the better, right? You want to be looking at MMLU because it is particularly highlighted since Chinchilla achieves around 67.5% average accuracy, significantly outperforming Gopher. The model architecture details here, which I'm only going to be going over the most essentials here. Parameter counts vary across a range from smaller to very large models to allow fitting the scaling law. Chinchilla itself has 70 billion parameters achieved by adjusting layer count, hidden dimension, and attention heads within a standard transformer template. Gopher, the earlier comparison model, has about 280 billion parameters. Like, why? Both are trained with similar architectural assumptions but different NND and choices. Fine-grained details like exact layer counts and dimensions matter mainly for reproduction, not for understanding the scaling law logic. Loss functions and optimization. As I said, loss, cross entropy, standard token level cross entropy between predicted and next token distributors. Optimization, we are using Adam or Adam W with standard settings used for large scale LMs with learning rate schedules carefully tuned so models trained to converge with respect to their token budget. The paper carefully avoids early stopping, so no early stopping function here. Noise when fitting the scaling laws by using losses measured when learning rate has decayed approximately, though layer commentary notes sensitive to this choice. Okay, the most important experiment here, which is scaling law fit and compute optimal frontier. This is the image that you'll see in the paper. Walkthrough, training grid, right? We train numerous models across range of sizes and tokens, ensuring overlapping coverage so the scaling law is well constrained. We then try to fit. They fit an empirical law that predicts the loss from N and D, capturing how both parameters and data improve performance. We compute the constraint, which is plug and play to fit into the compute constraint. And then we numerically find for each C the N and D that minimizes the loss. Then we look at the result, like I was saying earlier, and then the comparison. That compute optimal curve suggests that in the regime they study, you should roughly increase the data and model size together, leading to approximately X tokens per parameter rule of thumb, 20 to be precise, according to this paper. They plot existing models on this plane and show that many are undertrained relative to the optimum. This explains the backbone. Chinchilla is then a concrete test of the predicted optimum. Example result, right? Chinchilla versus Gopher at an equal compute. Please go back to the slide that says Chinchilla versus Gopher. Yeah. Essentially, compute budget, right? Gopher is a 280 billion beefy parameter model, which was trained with a certain total flops budget. Prediction was that the scaling law predicts that for same compute, a modality roughly 4 times smaller, which is 70 billion, as we observed, trained on approximately 4x more tokens, 1.4 trillion, accurate again, should be close to optimal. The action observed, they trained Chinchilla, 70 billion model on 1.4 trillion tokens using the same total compute as Gopher, and the evaluation gave a result that on MMLU, Chinchilla achieved 67.5% average accuracy, more than 7 percentage points better than Gopher, even though it is four-fold larger on the data set and 4 times smaller in the number of parameters, right? The action is, across many other benchmarks, language modeling, QA testing, etc., Chinchilla either matches or substantially exceeds Gopher, and even larger models like Megatron Turing NLG, which is a 530 billion RIP to their funders, and GPT-3, 175 billion parameters, RIP to their funders right now. Implications of this result. This validation both this validates both the scaling law and the compute optimal frontier. The recommended ND combination is not just theoretical, it yields a state of the art model, so SOTA, at lower parameter count and lower inference cost. Some performance trade-offs and limitations. Chinchilla has fewer parameters, obviously, like I've been saying for the last hour. So each forward pass is cheaper, inference latency and costs are lower. However, training more tokens increases training time and data engineering demands. So you need more high quality data, right? Which is like the whole point. The limitations are that scaling law is fitted on a particular model data regime. Extrapolating far beyond the regime can be risky. The law does not incorporate inference cost, memory constraints, or deployment specific objectives. Some contexts may favor larger models. Data quality and duplication are not fully disentangled. Later work shows that deduplication and distribution shifts can affect optimal tokens per parameter estimates, right? That's why I said never say once and for all, because more work will be done, more frontiers will be broken, new things will be contributed, and then you would be the fool sitting there thinking, oops, I was like the big brain, but now, I mean, you were the big brain, but like, you just got taken over and you just, made a claim that you were holding close. Assumptions and where the method might break. Some key assumptions. The architecture family, dense transformer decoder remains fixed. Parameter efficiency tricks or sparsity could change the scaling. The data distribution is relatively stable as you scale up. If you radically change the data quality or domain, the fitted exponents may shift. And training is reasonably well tuned. Learning rate, batch size, etc. So difference in loss reflects scaling rather than poor optimization. Potential failure modes of you know this work is if you move to highly different architectures, which is mixture of experts, retrieval augmented models, or compute loss relationship. The compute loss relationship may change and the same frontier may not hold. If pre-training data becomes saturated, example, you exhaust high quality web text, more tokens may yield less gain than predicted, so diminishing returns. For tasks where influence cost dominates, extremely heavy usage, you may want a different optimum that explicitly trades training compute against long-term inference compute. Some reproducibility considerations if you want to, reproduce this paper. If you want to reproduce this paper, the paper provides enough high-level description of the architecture and data sources to replicate the qualitative scaling effects. Each reproduction is difficult because the precise massive text-like data set is not public in all cases, obviously. Large-scale compute is required to trace out the scaling curve, RIP. However, several RIP to you. However, several later works and independent analysis replicate the basic tokens per parameter rule of thumb and approximate linear scaling of optimal N and D. Nice. Let's move on to the discussion prompt slide. How would this optimal frontier change if we cared primarily about inference cost instead of pre-training compute? Uh, that is something that we look at today, I feel. Like, pre-training was, taken ahead with this paper by DeepMind. I think today we are primarily caring about inference cost because there is too much. Like there's so much going on in the black box that we are just getting outputs, but we don't ask like why. I guess in those cases, architectures like retrieval augmented, and like something that can look into the black box and talk about like why, like you can infer the result that you're getting from an LLM. It becomes important. Does the Chinchilla scaling law still apply to modern LLMs trained with different data objectives or hardware? Of course, like I said, maybe not in all cases, but it does hold, right? Like we all know that your data quality does matter more than how big and beefy your. I mean, think about the brain example that we gave, right? Like you have a big brain, but you don't use it. You're not going to get anything, right? Like you don't study, you're not going to get like, the results. If you have a small brain and then you overextend it, of course you're going to be very amazing, but you're going to miss some things because you forget, right? Like token windows expire and our LLM start hallucinating. But yeah, it does hold. It just depends on the context and the situation. There is also the fact that if you were designing a new LLM project, how would you use this paper to decide your model size and data allocation? Honestly, I would just paste it into ChatGPT and then ask it, like, what do you think about it? And then I would ask my professor what he thinks about my LM results and my results and what I think. Let's move on to the last slide, please. And one final takeaway that I would have from this paper is for a fixed LM compute budget, for a fixed compute budget, data and training schedule are as important as parameter count. Many flagship LLMs have been undertrained. Reallocating compute toward more data and smaller models can yield better performance at a lower cost, right? Um, I would like to also leave you with a few fun facts, which is GPT-3 was trained on only around 1 to 2 tokens per parameter, drastically below the tokens per parameter ratio suggested by the Chinchilla regime. The paper implies that many early LLM efforts effectively spent compute on parameters that could not be properly trained with the available data. Chinchilla, though, achieves around 67.5% on MMLU, improving Gopher's performance by more than 7 percentage points, despite having one quarter of the parameters. Historically, this work sits in the lineage from early neural scaling studies to modern Chinchilla optimality rules that influence today's models like the Llama 3 and others. And why does this matter 5 years out? It has reshaped how labs plan billion-dollar training runs. It's not even in the millions anymore, making compute allocation more principled and helping explain why some newer mid-sized models punch above their parameter count. DeepSeek. um, some ideas if you want to take this research ahead. You could build a scaling law toolkit. You could do an empirical study of compute optimal training for instruction tuned or RLHF models. Um, Including cost-aware trade-offs amongst pre-training, supervision, reinforcement phases. You could also do a framework that jointly optimizes pre-training plan, data curation strategy, and inference deployment plan, all under a financial or energy budget. So just give this thing like limbs. For robotics or embodied AI, we can also think an analog to Chinchilla scaling for world models or policy networks. Now we are talking in multiple dimensions essentially. Um, for and yeah, I'd like to just close with this paper transformed how the field thinks about scaling. Instead of blindly making models bigger, it shows that under a fixed compute budget, the best models carefully balance size and data, and that many high profile LLMs were leveraging performance on the table by being undertrained. That insight made Concrete through Chinchilla's strong results now underpins how modern labs schedule multi-hundred billion parameter training runs and will continue to shape the economics and design of future foundation model. With that, I'd like to sign off on ARC session one. And yeah, thank you for joining us. I think this was um, a very fun read for me, at least. I don't know about you guys, but it was pretty fun. And yeah, we'll do this every other week. And uh, we'll just be building more on modern LLM. That's the theme for this semester. So it's a story that we are weaving together about. This is scaling law. We'll be going over another frontier topic, and then it's a story that weaves together in 6 chapters. But yeah, this was ARC session one.